This will be a complete review of everything that's in Dr. Murrow's Chapter 14 on conjugation, resonance, and dienes. Here are a few basic things about conjugation. It happens when there are 3 or more p orbitals that overlap. To do this, you need at least 3 sp2 carbons next to each other. If the pi bonds are separated by more than one sigma bond, it's not a conjugated system. Because of the delocalization, conjugated systems are much more stable than unconjugated ones. The reason why the carbons in the system have to be sp2 is so that their p orbitals can interact. Let's look at this example. Here are the hybridizations of each of the carbons in these dienes. Now let's draw the orbitals. On the one all the way to the left, the orbitals are going to look something like this. There are more than 3 sp2 hybridized carbons in a row, so this makes this one a conjugated system. Now if we look at the one to the right, it has one sp3 in the middle that separates, so these two can communicate and these two can communicate, but there's a break in between these. Because there's not 3 in a row, this one is an isolated system. It's much less stable than the one on the left. The difference in stability can also be seen through the heat of hydrogenation. These two molecules have the same end product, but the conjugated diene, the one on the bottom, has a smaller heat of halogenation. This means that it releases less energy, making it more stable than the one on the top. Delocalization is the reason why allylic carbocations are as stable as a secondary carbocation. The positive charge can be here, but it can also swap around and be on the other side. This gives us a hybrid structure that shows that the positive charge is delocalized over the 2 terminal carbons. Before we get into the 4 general types of resonance, you should know that an asterisk on an atom represents a positive charge, a negative charge, a single electron, or a lone pair. The first type of resonance we're going to look at is the 3-atom allyl system. If you have a double bond and an atom with some kind of charge, then you can swap the places of the double bond and the charge. Let's look at some examples. This one at the top is an allylic carbocation. This atom over here is X, this one is Y, and this one is Z. We can just switch the place of the positive charge and the double bond to give you a structure that looks like this. The molecule in the middle is an acetate anion. This oxygen is the X, this carbon down here is the Y, and this negatively charged oxygen is the Z. A pair of electrons from this charged oxygen goes and makes a double bond over here, while a pair of electrons from the initial double bond swing up to this oxygen to give you a structure that looks like this. Let's try one last one that might be a little more difficult. Which atoms on this last one at the bottom would you think be X, Y, and Z? Here are the correct places for the labels. Just like before, the lone pairs right here are going to make a double bond, while a pair of electrons from here are going to go back up to this oxygen to give you a structure that looks like this. If we look at the 2 structures from the last problem, we run into a pretty big question. What is the hybridization of the carbon highlighted in orange? On the first one, it's sp3, but on the second, it's sp2. This resonance structure can only happen if the electron pair on the carbon atom adjacent to the C double bond O can be delocalized. This can happen only if it has a p orbital that can overlap with the other p orbitals on the adjacent atoms. This conjugation can only happen with sp2 hybridization, so we say that this carbon is sp2 hybridized. The second type of resonance are conjugated double bonds. In cyclic structures like benzene, you get the 2 structures by moving the double bonds 1 over. For conjugated dienes, you'll get 3 total structures. In addition to the original structure, you can get one by moving the bonds to the left, and the other by moving the bonds to the right. The third type of resonance are cations with a positive charge adjacent to a lone pair. We're going to use the lone pair on X to make a double bond between the two, giving X a positive charge. Let's look at this example. This oxygen is going to make a bond between it and the positively charged carbon. This gives us a positive charge on the oxygen and a double bond between the oxygen and the carbon. The fourth and final type of resonance are double bonds with one atom more electronegative than the other. Let's look at this example. The carbon on the other end of this double bond is much less electronegative than the oxygen. So, a pair of electrons could go from this double bond to the oxygen to give us a structure like this. There are a few rules of resonance that we can use to determine what structure is the most stable. Structures with more bonds and fewer charges are more stable. Even though structure B does place the negative charge on the more electronegative atom, structure A has no charges due to the double bond, so it's more favorable than B. Structures in which every atom has an octet are more stable. Both structures have the same amount of charges despite one having a double bond, so we can't use the first rule. Even though the oxygen in structure B has a positive charge, all of the atoms have full octets, so they are more happy in B than they are in A. Structures with a negative charge on the more electronegative atom are more stable. Because the oxygen can handle the negative charge much better than carbon can, structure B is more stable. Here are a few basic things on conjugated dienes. They are compounds with two double bonds joined by one sigma bond, and they're also known as 1,3-dienes. They have 3 possible stereoisomers and 2 possible conformations. The single bond is unusually short. They are more stable and react differently than similar isolated dienes. They absorb longer wavelengths of light than isolated ones. A trans conformation is abbreviated as E, while cis is written as Z. To find the 3 possible stereoisomers, we are going to look at each double bond to see which direction their single bonds are pointing. Stereoisomers are abbreviated with Z for trans and E for cis. Let's look at structure A. The leftmost double bond has one pointing down and one pointing up. We're going to call this one trans. The rightmost double bond has one pointing up and the other pointing down. This one is also trans. We call this a trans-trans or EE13-diene. Now let's look at structure B. The leftmost double bond has one pointing down and the other also pointing down. This one is cis. If we look at the rightmost double bond, one is pointing up and the other one is also pointing up. We call this a cis-cis or ZZ13-diene. Now let's look at structure C. The leftmost double bond has one pointing down and the other one also pointing down, making it cis. The rightmost double bond has one pointing up and the other pointing down, making it trans. We call this a cis-trans or ZE13-diene. To find the 2 possible conformations, we're going to look at which sides the double bond is on in relation to the single bond in between them. We can have an S-trans or an S-cis conformation. Let's look at structure A. If we draw a line right where the single bond is, we can see that both double bonds are on the same side of the single bond. This makes it an S-cis conformation. If we look at structure B and do the same thing, we'll find that the double bonds are on opposite sides of the single bond. This gives us an S-trans conformation. Unlike stereoisomers, conformations can interconvert. If this cis molecule rotates here, it'll become the S-trans conformation. Let's review. If both double bonds have their single bonds pointing in the same direction, it is a ZZ stereoisomer. If both double bonds have their single bonds pointing in different directions, it is an E-E stereoisomer. You'll notice that the two isomers on the right are both trans-trans. So what's the difference between them? Let's draw a line along the middle single bond in both of them and see if we can spot a difference. The one all the way to the right has both double bonds on one side of the single bond. This means it's an S-cis conformation. The one in the middle has its double bonds on opposite sides of the single bond. This means it's S-trans. The two on the left are stereoisomers, while the two on the right are conformations. Remember that this S-trans conformation can interconvert to the S-cis conformation by rotating around its single bond. The reason why the single bonds in these conjugated dienes are so short is because of the S character. Let's look at this example. In the molecule on the left, there are 2 carbons, both of which are sp3. Out of 8 total orbitals, only 2 are S. This gives us an S character of 25%. Now let's look at the molecule on the right. The carbons on the sides of this single bond are both sp2. Out of 6 total orbitals, 2 are S's. This gives us an S character of about 33%. Remember that a higher S character means a shorter bond. Let's look at a few basic things on electrophilic addition. This addition yields different results depending on if the diene is conjugated or isolated. The product also depends heavily on the reaction conditions. Remember that kinetic is formed at higher temperatures and is formed faster than thermodynamic, but is less stable. Isolated dienes, like the one at the top, gives you one product. The hydrogen bonds to the less substituted carbon to give you a product that looks like this. If you do the same reaction on a conjugated diene, like the one at the bottom, you'll get 2 products. One is the 1,2 addition and the other is the 1,4 addition. Let's take a look at the mechanism to understand this a little better. In both products, this carbon attacks the H, which makes the electrons in this bond go to the bromine. This makes a resonance stabilized allylic carbocation. This negative bromine is going to attack the cation. Depending on the condition, it can add here, which is the easiest and fastest due to the proximity of the bromine to the carbon. This 1,2 product is the kinetic product. The bromine can also add a new bond over here, which is slower but more stable due to the alkene being disubstituted. This 1,4 product is a thermodynamic product. If you look at this chart, you can see why one is faster and less stable and one is slower but more stable. This red line, which is the thermodynamic product, has a higher energy of activation than this blue line, which is the kinetic product. This is why you get the red product more at higher temperatures. It needs more energy than the blue line to get started. Even though the blue line has a product that's easier to form, if you look at point B compared to point C, you can see that the end product is much less stable than the one the red line makes. Here are a few basic things on Diels-Alder's reactions. It requires a diene and a dienophile. It forms a new 6-membered ring in an exothermic reaction. The diene needs to be in an S-cis conformation to participate in this kind of reaction. The electron withdrawing group on a dienophile can make the reaction go faster. Endo-orientation is preferred, and the stereochemistry of the dienophile is retained. Let's take a look at this example. On the diene, which is the red molecule, we're going to label these carbons 1 through 4. On the dienophile, let's label this carbon A and this one B. We are going to draw 3 arrows in a circular pattern. There's going to be a double bond made between 1 and A. This scooches this double bond over here to the middle, and And we're also going to make a double bond between 4 and B. This gives us a new 6-membered ring that looks like this. Remember that to participate in this kind of reaction, a diene must be in the S-cis conformation. If you have an acyclic compound like this one at the top, you can rotate the molecule around the single bond. This will give you the S-cis conformation. If you have a cyclic compound, you can't rotate around a bond to change the conformation since it's locked in. It has to already be cis to react. This means that this compound can undergo this reaction, while this one cannot. Remember that dienophiles are electrophiles. This means that if you have an electron withdrawing group attached to it, it will be even more reactive. A common group is a carbonyl group since it has a partial positive charge. These groups are going to withdraw some of the electron density from the double bond. This means that if Z is an electron withdrawing group, compound C will react much faster than compound A. Remember that the conformation of the dienophile, not the diene, is retained. If we look at this reaction happening at the top, you'll notice that the dienophile is cis. Let's draw the arrows like any normal reaction. Because the dienophile is cis, we're going to have to put these two substituents going in the same direction. This will give you a mesocompound. If the dienophile is trans, like this reaction at the bottom, you'll get a pair of enantiomers. Let's draw the reaction arrows to make the 6-membered ring. Because the dienophile is trans, we're going to have to put the two substituents going in different directions. If you have a cyclic dienophile, you're going to get a bicyclic product, also known as a fused ring system. Cis-fuse happens when the carbons are adjacent. The hydrogens are going to be in the middle of the two rings. Bridged happens when the carbons are non-adjacent. You'll have to figure out if the substituents are exo or endo. If the two atoms that are shared are adjacent, you're going to form a cis-bridged system. Remember that the two hydrogen atoms on the ring are going to be cis because they're like that on the dienophile. Let's label these carbons. As usual, we're going to make a bond between 1 and A and 4 and B. Remember that these two hydrogens over here need to be put on the ring in the same direction since that's how they are on the dienophile. You can put them either both facing forwards or both facing backwards. If the carbons that are shared are non-adjacent, you're going to get a bridged ring system. Let's color code these carbons so we can track their movements a little better. As usual, we're going to make a bond between 1 and B and 4 and B. Here is our product. These 4 carbons right here are from the diene, and these 2 are from the dienophile. This carbon in orange is facing us right here. This result can also be drawn in the chair conformation. Here are the carbons color-coded so you can see where they are. When you have a bridge system with non-adjacent carbons, you have to figure out if the substituents are exo or endo. For this reaction, you can place Z in the endo position, closer to the 2C bridge. You can also place it in the exo position, closer to the 1C bridge. Because of the transition state that happens with endo addition, it's the more energetically favorable arrangement. If you need to find the reactants from a product of a diene reaction, first find the 6-membered ring with a double bond. Then draw the 3 arrows around the ring to put the bonds back to where they were before. Make sure to keep the stereochemistry of the substituents on the dienophile. Remember that cis substituents give you a cis dienophile. Let's look at this example. The six-membered ring is obviously right here. Let's draw the arrows to show that the bonds are moving back to where they were. This bond in the middle goes back over here. This bond breaks apart the two molecules, and this one goes back over here. If we look on the substituents, we can see that both of them are going in the same direction. That means our dienophile is going to be cis. Let's keep that in mind when drawing our reactants. Let's take a look at this example that's written in the chair conformation. First, let's identify the six-membered ring. Now we'll draw the three arrows to show the bonds going back to where they were. If it helps, we can label the carbons as 1 through 4 and A and B. Here are our two reactants. You can also draw this out of chair conformation to give you a diene that looks like this. Before we finish, let's look at a few things on UV light absorption. Frequency is directly proportional to energy, while wavelength is indirectly proportional. Because there's such a big difference in their ground and excited states, stigma bonds and unconjugated pi bonds need higher frequency of lights to be promoted to the next energy level. Conjugated dienes don't need as high a frequency because there's not that much of a difference between their two states. Wavelength max is the wavelengths of a light a compound absorbs. If a compound is conjugated enough, it'll take on the color of light it doesn't absorb. Congratulations, you have made it to the end of chapter 14.